Thanks everyone, thanks to the organisers for giving me this opportunity to tell you about some of the PhD work I've been doing with Charles, and thanks to Charles for the introduction to the method. So I'll just take you straight into the numerical implementation of what Charles just spoke about. So we're interested in how inhomogeneities impact observations, in particular the flow across the sky. And so Charles just described this method for calculating this flow, and here we're going to apply it to Szekeres models, which is an exact solution of the Einstein field equations. And then I write code in MATLAB to solve these propagation equations and then calculate the resulting observables. So then we can build some models and see what we get from them. Okay, so this is the Szekeres metric. I'm not sure if you're very familiar with it. It's kind of a big mess. It's a little bit like the LTV solution in that, but it's more general than that. So it's got no spherical symmetry. Let's see. So this R over here is something like the areal radius, similar to LT models, and it obeys something like a Friedmann equation, except I'll say that this is a function of time and radial coordinate. And in addition to LT models, we have this other function E, which in some way controls the non-spherical symmetry. It's essentially the inhomogeneity away from spherical symmetry. And so we have four coordinates, T, R, P, and Q, and these P, Q coordinates in fact need not be what you think of as the PQ2 surfaces are in fact not necessarily spherical as in LT models. They can be, depending on the value of epsilon, you can foliate space-time with spheres, or if epsilon is -1, you can in fact foliate space-time with hyperboloids, which is kind of odd, and these models haven't been investigated all that much. So that's this epsilon. It controls the foliation shapes of the PQ2 surfaces. F is related to the energy, something like the E function that Jose was talking about yesterday in LT models. M is the mass within some radius, so it's kind of easy to think about that in the spherical case. So we have basically 6 metric functions here. 3 of them are common to LT, the mass, the curvature, and the bang time. And then these 3 new ones which control the inhomogeneity of how you arrange these two surfaces.
So why do you assume they only depend on R?
Yes, these, excuse me.
What's the symmetry?
These only depend on R. Yeah, but why?
Yeah.
Well, so depending on how the 3 of them vary, they control, let's say, the orientation of the dipole on the 2-sphere. So in LT, you just have constant density on a 2-sphere, and as you go out, you can vary the density. In these models, the 2-sphere can have a dipole, and the orientation of that dipole is controlled by these 3 functions. So they are only a function of R, but they do allow you to control, in a sense, where the overdensity and the underdensity sit in terms of these PQ coordinates. So if you look at these projections here, S, P, and Q determine how the 2-sphere maps to the PQ coordinates. So in a sense, moves the origin around of these of how the mapping between the two. Yeah. So it's a stereographic projection. Okay. So once we've defined our model and we've defined these 6 arbitrary functions, the space-time is fully specified. But we, of course, don't want any shell crossings, so we have to check all this big mess of conditions. This is just for epsilon is +1 models. There's a whole set of different conditions for epsilon is -1. So it's a big mess. And just to remind you of the picture, we're setting up the basis vectors here at the observer, propagating them down the light cone to the emitter, and then calculating the observables from that. So how do we do this? We have, of course, have to solve for the light cone, so that's the null geodesic equation. So this is 4 second order DEs in terms of components. And then the geodesic deviation equation, which is in fact 16 second order differential equations in terms of components. So in total we need 40 initial conditions for all this. And in addition to that, we need these guys, the Christoffel symbols and their partial derivatives. And if you saw the metric earlier, you'll know that this is going to be a really big mess. So this is the Maple and GR tensor, and they can do it all for us, but you come out to something like 104 partial derivatives of these symbols. So it's an incredible mess. And if you try and perform these contractions in MATLAB, it turns out to not work so well. Lots of cancellations and things. So we symbolically simplify the geodesic deviation equation in Maple. So we substitute all these in and expand out the contractions. And then you get this. So now this is in fact just one component of the geodesic deviation equation. But it's now explicitly written in terms of the metric functions, up to second derivatives of the metric functions, because we've got partial derivative of the Christoffel symbols. And because E and R appear in the metric as derivatives, that means we need third derivatives for E and R. E is quite trivial, it's an analytic expression for that, so we can take all the third partials for that. R is a little more involved. So the evolution of R depends on the value of F, the energy or the curvature. And so there's 3 solutions, the hyperbolic ones, parabolic and elliptic, depending on the value of F. Only in the parabolic case can you write R explicitly in terms of T. In these 2 cases, you actually need to do some interpolation methods to, given the metric functions, determine this eta value, the phase parameter, and then plug that into here to determine R. And numerically, things will never be exactly parabolic, so this is never really going to come about. And as you get close to parabolic evolutions, you find you get numerical cancellation of large, nearly identical terms, and this causes a lot of error. So what we do is we do a series expansion for the value of R for a parabolic evolution, and we make flat borderlines so that to avoid this large numerical error you get when you approach parabolic evolutions. In addition, we need to sort of compactify the range of eta here, because for hyperbolic evolutions, eta is defined from 0 to infinity. And of course, you can't interpolate or define a spline curve over this range numerically, so we write t equal to hyperbolic tan over eta. So we can rewrite this equation in a way that we only have to spline over some finite range. So now I think we've got expressions for R, E, and the propagation equations are written in terms of those and their derivatives. So we're there now. We've got all the expressions we need, except we just have to get derivatives, the various partial derivatives for R, which I don't show here, but it's quite complicated.
And for those expressions, you're assuming dust.
Dust. Okay, so now I think we're in a position to solve the equation. This is just to show you very simply this program structure. You initialize the variables, propagate the basis vectors, calculate the observables, and then interpolate this at some constant redshift, and then just loop over the whole sky. So but most of the program is actually in this block here. That's where we solve all the big mess. Okay, so now I'll just show you some preliminary results from what we've gotten so far. Of course, the first thing to do is test the Robertson-Walker special case. So Szekeres contains Robertson-Walker if you set the metric functions to this form. So having the mass go like r cubed and the curvature like r squared. But one need not have these special these Szekeres sort of inhomogeneity functions being constant. They can actually vary, and you still have Robertson-Walker. It just does really strange scaling of the coordinates and stuff. Okay, so we do a run like this. We place the observer somewhere in space-time, and so this is T and R. So it's here, it's a circle, and each line here is a light ray we've shot in some direction. And this black line here is the Banning surface. Okay? And these constant black lines here are lines of constant redshift, these lines here. Okay, so this is not very physical, it's just coordinates. It's more coordinates, PQ coordinates, not very physical. Okay, but here we now construct the area distance along each light ray. So there's 200 light rays, and they all lie on top here, which is great. And this is the error between a known analytic solution and each of our light rays. So it scales really nicely with the integrated tolerance, so this has got some indication that it's converging to the correct result. And here's what we get for the flow across the sky. So this is for all the light rays. Of course, in Robertson-Walker, we don't expect any flow. And you can see that this is in fact numerically zero. It's scaling with the integrated tolerance. As we tighten the integrated tolerance, these just get smaller. I've converted it to units of milliarcseconds per year. So this is 10 to the minus 4 milliarcseconds per year. And as we tighten the integrated tolerance, this just goes to zero. So then we can go to spherical symmetry and check out an LT model. So now we just take the same as a Robertson-Walker model, but add a mass perturbation somewhere near the origin. And so this is actually a void model. And we place the observer somewhere away from the origin, looking at the void. So here's the light cone. It's kind of weird because this is in a radial coordinate, so these radial coordinates, so R is in fact going past the origin, and it's like with some impact around it. It's not very much consequence. This is the density. You can calculate the density along the line of sight. So all the light rays, of course, the density is increasing as you go back in time. But you see here in fact, two light rays go through this void around a redshift of around 0.5. So what does this do to observations? Well, the diameter distance is much the same for all the light rays, but if you plot the relative difference between them, you can see the effect it had on the one light ray that went forward. In fact, there's two here, on the two light rays that went straight through this void. But it's relatively small. This effect. I will say it's not a huge void. If you look at this is the relative density. Well, this is the difference between the density between various lines of sight. So it's not a big density contrast.
So the observer is the space with the spectrum center.
Yeah.
What about moving towards the center? Did you try that?
So he's co-moving with metric coordinates, with the flow, local flow. We can boost the observer if we like.
That's what happened.
Yeah. We haven't tried that yet. But he will be co-moving with whatever flow there is, I believe.
I think like CME dipole will be different.
Okay, so now that we've got the area distance along all the lines of sight, and we know that those lines of sight are a constant direction for the observer, we can make sky maps. We can interpolate a constant redshift, basically slice here and generate sky maps. And this is what we get. So this is what you'd expect from a void model with an observer away from the center. It's actually symmetric on the sky. I apologize for the low resolution. This is just the amount of time I had to do the runs. But of course, if you add more points to the sky, these lines should get a bit smoother and clean up a bit. And this is the flow. So again, we're away from the origin, looking at a void. And these are the two lines of sight you will go through the void and affect the area distance. So you can see there's some appreciable flow here around this void. This is in milliarcseconds per year again, so this is like an arcsecond a year. For something that gave a relatively small deviation in the area distance, we're getting quite a lot of flow. So then again, we can build maps with this, and you get something like this. So this is just at a particular redshift slice, 0.3, so somewhere here. And you see something like this. So the void's expanding, matter flowing outward. And then there's also this strange effect of things seem to be flowing toward the void and away from, this is the antipodal point, so this is behind you.
You don't really need to have 6 significant digits in redshift, right?
No, not at all. It's just, yeah, plotting. Yeah. Okay, so now we have an indication that we're getting what we should expect. Robertson Walker looks good, LT looks kind of good. And I'll just show you one set of results from Szekeres run with some full inhomogeneity. So now the metric functions, the LT metric functions are not Robertson Walker, and we've got some variation in the angle of the dipole. So what you take, don't worry about all of this except to take away that there's dipole variation and it's not just spherically symmetric. So here is the light cone. Again, this is now the Wang surface doesn't need to be constant, of course, in these models. So this is the Wang surface. We make it varying. So here's what we get for the area distance. It's quite. So I will say that this is by no means a physical model of the universe or anything. We're just sort of trying to see what we get by running the program with some inhomogeneity. So this is what you get for the area distance. You see some appreciable variation across the sky, as well as for the flow. So then we can translate these into sky maps and then just slice them through at various redshifts. So I'll just get through those, and you can see. So this is nice. You can see that it's not spherically symmetric, right? There's an overdensity here, I think an underdensity here, or something like that. And then the flow, we can do the same thing. And we start with redshift 3, but in principle you can go further. And so again, you see the non-spherical symmetry here. So this is a nice indication that we think that our method's working. And I think I'll stop there. Yeah, so we've developed this method, we applied it to Szekeres, we wrote the code in MATLAB, and then we've done some runs. Robertson Walker seems to agree really nicely with the analytics. LT qualitatively agrees in that we know what we should see in a qualitative sense. And the Szekeres runs show some interesting behavior, but of course there's lots more to do here in terms of model building and seeing really what sort of patterns we can get on the sky. And it would be nice to model some, like Carl said, some local structures in the universe and see what to expect. But I'll stop there.
Are there any exact solutions to Szekeres that you can compare with your numerical calculation?
Are there exact solutions?
Yeah.
For
LTV, we know that there are.
Yes, so LTV there are. I'm not sure that in Szekeres there are in general. You'd have to maybe set up a very sort of symmetric situation, put the observer at some symmetric position. In that case, there may be, but I'm not so sure.
Have you tried that?
I'm not sure. No, I haven't compared with the analytic Szekeres solutions.
You mean analytic solutions for light rays?
For light rays.
What do you mean by exact? I mean, Szekeres is an exact solution. So, are you looking for solutions for light rays?
The nonlinear solution from GR in Szekeres metric, so that you could compare shapes from your metric.
The metric is an exact solution. But if you're looking for solutions for light ray paths, that's a horrific problem. There wouldn't be any exact solutions unless you oversimplify it.
I think what one is asking is whether we have sort of solution analytical expressions for the RFT, RFTR, the functions that appear in the metric. Are there situations in which we know some analytical expressions for this exact solution that Szekeres used?
Analytical solutions for
so the evolution function. Yeah.
With area distances, you can compute, right?
The area distance has to be.
Contours that you can show them, you can compute, right?
Analytically, I mean, not in general, I wouldn't say.
The functions of the metric itself you can solve exactly. This is the solution actually for 0 lambda. It's parametric solution, but that gives the main evolution function. And then the 6 arbitrary functions you choose at will. But area distance, again, because the metric is inhomogeneous, there is no hope of getting an exact solution.
So, yeah, these things we can get an exact solution for, but not the result.
But the special cases like LT we can do, yeah.
While writing the program, have you kept this capital P, capital Q, or rather E, which is the non-spherical part, small with respect to something, or it's arbitrary?
Epsilon, yeah.
No, this capital E, I mean, which gives the non-spherical.
Right.
Yeah.
So
is it small or?
No, not necessarily. In fact, we try to get it as close to shell crossings as possible, just to see. In some instances, we've tried to push the inhomogeneity as far as possible before getting a shell crossing to see what you get. So there's lots of freedom to choose this, and then I'm not sure what the value of that would be.
What is the exact definition of M?
M is the same as in LTB, I believe.
Okay.
Yeah.
So, you did this for dust.
Yeah.
If you had something else with pressure, would that be prohibitively influencing your code, or could you?
Well, you'd have a different metric, of course. That's the measure metric, I believe. It's increased pressure. So this would be different. All of these guys would be different. And this would be different. So yes, it would be very different.
Is it feasible? Is it feasible, or would it?
Yeah, in principle, you can apply this method to anything that you have an analytic expression for, let's say, the metric and the Ricci or the Riemann curvature tensor. So you can analytic expression for that thing.
It's very difficult to find analytic solutions with non-zero pressure. The Lemaitre solution isn't really a solution.
Oh, really?
You can integrate one equation, but not the whole lot.
Oh.
What about just lambda?
Plain lambda.
You did right there an equation where appeared lambda infinity, right? That lambda is the cosmological constant.
Yeah. So this is.
So it's a special pressure.
This is the evolution of R with lambda.
Right.
But I'll say that we haven't included lambda here, because if you include lambda, these solutions for R, these guys become different. Yeah.
They become hypergeometric functions.
Yeah.
Does the code slow down at all if you have more complicated distributions of matter? So I'm thinking that there are these recent papers by Belezhko and Sussman where they have extremely complicated solutions that they claim fit into Szekeres. Could you take any arbitrary complicated distribution like they have and put that into your code?
In principle, if it fits into Szekeres, I think so. Yeah. Not sure how long it'll take to run, but.
Just a technical question. Is it easy to estimate the numerical error in MATLAB? Does it scale with some specified power of?
So, as an estimator, we sort of looked at the deviation of the area distance and from its analytic solution in Robertson-Walker, and then sort of tighten the integrated tolerance and just check that it sort of scales with the integrated tolerance. And aside from that, yeah, it's hard to know how much to trust observations, of course. I mean, I have to trust numeric. This gave us some indication that, as you scale the relative tolerance of the integrator, this area here is pretty much scaled with it.
But you haven't measured how it scales. You're just looking at it as smaller.
Yeah, it's kind of preliminary. Yeah.
So, do you foresee, it's a bit of a follow-up of Tim's question, do you foresee some cosmological applications of this whole procedure?
Well, yeah, I guess there's a bunch you can do with it. Cosmological applications, I suppose, like David Wiltshire and co have done some interesting things with similar models and looking at the CMB dipole and whether it's really like a relativistic thing or if it's just a boost, or if it's something like, or if, say, some really super Hubble structures exist, to know how these maybe affect, how we look at CMB or...
So you have those things in mind?
Yeah.
You can make structures that look like the things that Charles was showing, where you have the superclusters that are...
there's this
something that's largely similar.
This paper by Christoph and
Yeah.
If I might add, I think one of the things is whether or not, you know, we confirm homogeneity on the largest scales, I think just checking that involves checking not just simple variations, but even more subtle ones. And I think that even as, if it turns out to be a confirmation of homogeneity, I think it's still worth looking at the effects on cosmological scales.
Okay, and Tony, of the